Entropy is the second major topic that we're going to discuss when we're discussing thermochemistry. The symbol for entropy that we're going to be using is S, and I really don't know why. Entropy actually stands for chaos or disorder, or the randomness of a system. So as you can see in this cartoon, his office is awfully messy, thus a high amount of entropy. So here we have it defined. Entropy is the measure of disorder or the randomness of a system. Or another way of thinking about it is the chaos. It's the opposite of order. It's the opposite of structure. Now the second law of thermodynamics states that everything has a tendency to move towards disorder. And that stems from the Big Bang Theory, in which we had a massive grouping of everything that was in the universe, and it broke apart in one instant. And since that instant, everything is beginning less and less close to one another, thus less and less structured. So it's reasonable to assume that the entropy of the universe is always increasing. Here we have a couple cartoons that actually play on entropy and its meaning. I'll give you a second to digest these, and then we're going to move on. I personally love this one over here. It'll take you a little bit to get, but once you do, it's pretty funny. Okay, the equation that we're going to use for entropy is very much the same as the equation that we just used on enthalpy. The only difference is we're not measuring the heat content, we're measuring the disorder, the randomness. Now, like enthalpy, the constants for these are based on the constituents that make them up. So, for example, when you think about chaos in terms of the states of matter, you think about a gas. A gas is going to have a higher disorder measurement than a solid would. So these are constant values. They're also provided on the thermodynamic properties sheet that's available on the class website. A value obtained from this of a positive delta S means that we're going to be increasing our disorder. Another way of thinking about this is we're becoming less ordered. More disorder equals less order in organization. The opposite is true of a negative delta S. A negative delta S would show us that we are decreasing our entropy. So here's an example problem you might find. First thing you want to do is balance the equation, but upon checking, you find that it actually already is balanced. And so ultimately what we're going to be doing here is using the constants for each of these values to obtain a product side entropy and a reactant side entropy, which we will then subtract. So I've set up the problem where 1 mole of sodium chloride multiplied by its entropy constant gives us that, 72.13. Added to the other product, water, we come up with a total value of 142.04 joules per Kelvin. That is the measure of disorder of our products. The measure of disorder of our reactants is 56.5. When we take our products in green and subtract our reactants in red, we find that we come out to a final entropy value of 85.54 joules per Kelvin. Because this is a positive value, we can state that the products are more chaotic or more disordered than our reactants. Therefore, we have increased in terms of our disorder in our process. There are also ways of looking at an equation and using clues in the equation to figure out what our product is going to be in terms of its disorder. The first thing we can look at is whenever we have a change in the state of matter for the same substance. If we're going from a solid to a liquid, or a liquid to a gas, or a solid to a gas, we're increasing the amount of disorder of the particles that make it up. Therefore, we're creating a positive delta S. If we dissolve a gas, we're kind of like caging a bird. A bird can fly free in the sky. But as soon as we put it in the cage, we can confine it to a very small area. So we would be decreasing the chaos of that gas. Another example from that is the carbon dioxide that's stored in pop. It's dissolved in the liquid, and it's not until you pop the top where you actually release that gas in the form of carbonation. Whenever we have a state of matter, or whenever we do not have a state of matter change, entropy will increase when the number of gas particles in the product is greater than the gas particles in the reactants. So gases are the most chaotic, the most disordered. So if we are making more in our product than we had when we had our reactants, then we're going to be increasing our disorder. The opposite would also be true. Whenever we dissolve a solid into a liquid, we're also increasing its disorder. We're doing so because we're actually liberating it from its organized structure and allowing it to flow freely in the form of a liquid. And finally, anytime we increase the temperature, we're providing more energy, and more energy leads to more chaos. So anytime we increase our temperature, we will increase our delta S value. So here we have a picture of the three states of matter. The lowest entropy is going to be on this end, and the highest is going to be over here. To get from one end to the other, add heat. Here we have an explanation, an example of entropy.